This meeting is being recorded.
All right, so yeah, maybe David, maybe you can mute yourself and then we'll... All right, yeah, so Nick, you're next. Yeah, tell us more about bodo.ai.
Thanks so much, Florian. Thank you, David. That was a very interesting talk. I never really thought about the inner workings of what it goes to trying to defeat the resume automation software. Very fascinating. So hi, everyone. Thanks so much for coming here to listen to me talk. My name is Nick Riasanovsky. I'm a senior software engineer at Bodo.ai, and I work on our core engine team, and in particular, our inferential compiler, which is a concept I'll explain throughout the course of this talk. And essentially, we are building a new data platform to provide supercomputing performance to Python data analytics. And I'm going to walk through some slides to kind of explain what that means. And then I have a demo to show at the end on our SaaS platform. So, okay. So the basic problem that we want to address is the fact that what we've found is when big companies or when you scale to big data, typically there's a rewrite process that engages from going from the initial development to the ultimate production deployments. And our ultimate goal is to be able to provide HPC or high performance computing, the quality of parallelism you get from running code on supercomputers, to general data analytics into the general world, right? But as we see it right now, we find that developers typically love to start in Python. They love to use pandas, NumPy, other open source libraries. They'll initially begin on their laptop, and they'll do that because Python's simple and Python's great. But what big companies will do is they'll invest in data engineers who will go through the process of rewriting this code into scalable systems. Because as much as we love Python, we know that you can't just deploy a Python script across thousands of cores and scale to like terabytes of data. For these things, people convert their code to C++. They convert to Spark using Scala or Java, and their data switches from something you tested on your machine to your cloud file systems. And with Bodo, we believe we have a solution to this problem. And I'll show some examples in a little bit. But basically, Bodo is offering an opportunity to do your development and your production code still in Python. And what Bodo will do is it'll scale out your production Python, your development Python into production code. And we do this through our high performance data storage connectors. So no matter the file system you're loading from, if you're loading from S3 or you're loading from a Hadoop file system, you'll get the same performance or great performance, just like you would on your local files. We provide automatic parallelization, meaning the same code that you run locally on your laptop can scale automatically on clusters of machines. We additionally offer the ability to have end-to-end optimizations. So those little code segments that seem to work well, those will work well when they get to the full production workload altogether. In addition, we offer high-performance analytic primitives and integration tools so you can integrate us into your system. And so this is an example of what Bodo code looks like. So on the left here, we have some code that came from a major exchange. And what they want to do essentially is search a stock ticker and then compute some statistical information based on that. That's what this describe function does. It computes a lot of stats like min, max, among other things. And this code is all just traditional pandas code, right? This is read parquet as a pandas function. All of these are just pandas operations. But pandas is, it's a single core library. It runs well on your local machine, but when you're scaling up to larger amounts of data, it's not a possibility. So all we did to change this code is we added this Bodo JIT decorator, and that tells Bodo to compile this code into a parallel binary. And to do that, we're compiling this code into an MPI process. MPI stands for message passing interface, and it's essentially the way of programming that people write code on supercomputers. And it's incredibly efficient, and it's truly parallel code. And so when this is done, this goes from something that can only run on one core on a single machine to able to scale to, we scaled it to 4 nodes, and we saw 115 times improvement, as opposed to just running it on a single machine. And this is the goal of what we want to provide to people through Bodo. One thing you may note about this, if you're familiar with the open source project Numba, this looks very similar to Numba code. And that's because we use Numba internally in the process of building our compiler. For those of you who aren't familiar, Numba is an open source Python project for building compilers. It's a compiler toolkit, and it's also used for scientific computing. And it's a project we love to support and we contribute to regularly. So where we see Bodo as fitting into your infrastructure is helping to provide people with access to a truly dynamic situation where you can reuse, and deploy Bodo in a variety of situations without necessarily the same vendor lock-in you get from transitioning entirely into a library-based solution. So we support open source Pythonic APIs. When you're programming in Bodo, you're using Pandas APIs, you're using NumPy APIs. So the code that you're using is the same code that's done in development. And so if you ever decide to deviate from that, you're welcome to do so. You're not being transitioning entirely into some proprietary library that you have to transition all of your code from. We work with a variety of data sources. So you can load data from Parquet, you can load data from S3, you can load data from Snowflake. And we work on all the major cloud providers and as well as on-prem, although we have a SaaS platform that's available primarily through AWS with some limited availability through Azure. And we do recommend running through that because it makes the process seamless, because no matter how well Bodo is able to make your code process scaling, there are still significant challenges that come with maintaining clusters of machines. And my experience has always been that nothing on-prem works as intended initially. So I've talked a little bit about what makes Bodo appealing from a utility productivity perspective, but the actual thing that we hang our hat on in terms of wanting to give the HPC performance to Python developers is our ultimate performance. So we had a customer who's a Fortune 10 company, tech company. They ran this benchmark, TPCxBB Core 26, and this is a open source benchmark that's meant to emulate ETL, data prep, and a particular featurization of analytics and ML workloads. And so they ran this with the scale factor 40,000. And what that means is if you load all the tables into memory, it should take roughly 40 terabytes of data. And they run this across 4,500 cores, and they found that Bodo was 20 times faster to running the same workload in Spark. And that's really the performance advantage that we're aiming to provide with Bodo, is when you have things that are scaling to be 20 times faster, those are huge infrastructure savings, those are huge energy savings. And ultimately, we believe that can transform the way that you do data analytics. So the way that we accomplish this is through our inferential JIT compiler. And this is what I work on a significant amount. So I don't know how familiar everyone in this audience is with what a compiler does, but at a very simple level, what a compiler is doing is it's essentially converting human readable code, say your C code, into some sequential code in order to produce a sequential binary. So your C code gets compiled down into instructions that run on your x86 processor, for example. What Bodo's inferential compiler is and what makes it fundamentally different is because of the semantics of data analytics operations, for example, joins across tables, Bodo makes decisions about how to generate truly parallel code. So we determine the relationship between these operations, and then the binary that we compiled is compiled into a native parallel binary with MPI, as though you'd written these libraries with MPI code yourself, right? And that's what makes us fundamentally different from anything else in the space, which is more of a library-based solution. So before Bodo existed, all of the existing alternatives in this space, they're not using a true parallelism model. They're using more of a distributed model. So we have an example of what the architecture for Apache Spark, Dask, and Ray look like on the left. And these are what are commonly referred to as driver executor models. And what that means is you'll have some code, in whatever their Pythonic-like API is. The driver program will execute that code sequentially, and it'll essentially construct a graph of tasks. And these are, the various tasks that will be executed by all of these executor processes. Then the driver goes through and assigns these tasks repeatedly, and then results get computed. And this process, continues driver assigning, executor assigning results throughout the life of the program. And in the process of doing this, there's this constant communication between the driver and the executor, and this constant overhead of scheduling tasks. And that's what we call a wave of tiny tasks. And it actually ends up being a pretty significant overhead. And that's one of the fundamental reasons we believe that on that previous slide, you saw that difference in terms of the speed between running Spark and running Bodo. It's that fundamental overhead. In contrast, if you look at the right, the architecture that Bodo has doesn't have a driver at all. The code that's compiled is natively parallel. All of the communication between processes is baked into the compiled code. And as a result, there's none of that overhead. And this is why we believe that Bodo is a true parallelism solution and is the fundamentally right way to do parallelism. And so because of this, what we really believe is that Python should be and can be a first-class language for big data and data engineering. And that this model that potentially exists of templating solutions in Python before eventually converting them to production ways of doing the workloads, that doesn't need to exist. And Python itself can be used all the way from development into production. And for the next couple slides, I'm going to go through some of the things that Bodo does. It's a little bit of an introduction to kind of how our parallelism model works. There's a lot more detail on our website where we go through a tutorial where you can see some information about how to get started with Bodo. This should give a nice insight into what Bodo does differently. So the first thing I want to talk about is scalable I/O. And so what we've noticed is that when it comes to scaling your solutions, one of the first pain points that people have is just trying to load data. It's a consistent problem. it's always difficult to, have a solution that scales if you can't load the data that you need. So Bodo has placed a particular emphasis on having these high performance data storage connectors in order to ensure that we can, successfully load data in a very efficient manner. And so this is a little bit of a diagram that kind of shows our general parallelism model. So if you're loading data from Parquet files, or you're loading from CSV files, if you're loading them from SQL files, there are a set of processes that are used to execute this code, and each one is just loading the chunk of the data that it needs. And so the Bodo parallelism model is really each process maintains a chunk of the data, and then when you encounter operations that require communication, across various processes, for example, like joining two tables, then at that point there becomes a communication and a data exchange. But each process is essentially managing and maintaining its own chunk. One thing I do want to emphasize is, the previous example shows a really good example of what we would say is seems embarrassingly parallel, of just splitting things and having each process, manage their own chunk. What we, to give you a realistic use case, what we find is that when you get to these actual system levels with scaling, there's a lot of devil in the details in terms of what can go wrong. And a really good example that we have of this is if you're trying to, say, load from a data warehouse using like a SQL connection, the simplest thing that you could think to do would be to partition your SQL query into many parallel queries. But what we found is that more often when this happens, these warehouses tend to just fall over. There are too many queries that are queued up. It slows down the warehouse and you're unable to do anything efficiently. So these are the problems that we talk about when it comes to just loading data at scale. So what Bodo does, and we work with Snowflake, we have a partnership to work with them, is we've put in a significant amount of effort in terms of making sure that Snowflake data can be loaded efficiently inside of Bodo. And to do this, we've taken advantage of their new distributed fetch connector. And what the Snowflake connector does is it enables using a single SQL query in order to load data in batches in arrow format. And then each of our processes can load the chunk of the data that they need and efficiently continue to proceed without worrying about these, big data scaling problems of how do I make sure that my IO loads effectively. To elaborate a little more on what Bodo can do with Snowflake and with SQL in particular, is we believe that Bodo can be a solution for helping to transform the user experience and help to ensure that you can see great performance, in most situations. And one of the consequences of this is, typically speaking, when you go through the process of loading data from SQL, you have to be very careful about how you've done these SQL queries. If anyone has ever manually, gone to like a SQL connector, they've loaded the data, and then they continue to do processing in Python, then you probably know that basically whatever that query says is what gets executed. So if you were to do something like try to load an entire table, which is what this query does, that would be a big no-no because you'd essentially be loading all of the data. But with Bodo, Bodo's actually able to figure out how you're using the data in this situation. So it sees that there's a filter that's being applied to the data that could be done before the data load. And simultaneously, it sees that the only actual column in this table that's being used is column B. And so what Bodo does with its Snowflake connector is it transforms the SQL query that's being executed. We're not just executing, selecting all the data from the table. We update it to apply the filter directly and then select the only columns that we actually need. So in this way, we at a minimum, help to improve the user experience because you don't have to worry about spending all this time to optimize your SQL queries. But in some situations, we might be able to track things that aren't necessarily trivial to consider and help to make sure that your data load is effective. Now, Bodo is a project that has limitations. All projects have limitations. I want to talk a little bit about what those are. So Bodo uses compiler technology, and as you're probably aware, Python is not a statically typed language. It's a dynamic language. And so as a result, there are situations that can arise where it's not necessarily possible to compile everything. So here are a few examples of situations that can cause issues for Bodo because of the lack of type stability. So if your variable changes types, that can be one potential problem. If it's not possible to statically determine the function that's being called, that can be another problem. Or if your data frames themselves have inconsistent schemas because the schemas lead directly to typing inside of Bodo, that can be another situation which can cause problems for Bodo to compile code. And so what we've tended to find is, typically speaking, there are ways to transform your code just using native Python to make sure that it's type stable. And oftentimes, if you write good, clean code, you won't run into a lot of the issues that can occur. The development of Python has been a lot of, adding type hints, adding information about typing. And so we think things have transitioned a lot in a way where if you're doing things the right way, you'll typically write code that's capable to compile in order to perform. So before I hop into a demo, the last thing I want to do is go through in some detail some benchmarking numbers of Bodo in comparison to some of the other projects that are out there. We talked about Spark, Dask, and Ray earlier, so we're going to look at some benchmarks that compare them. So one thing that happens with any of these projects is they always promise speed and scalability, but oftentimes there isn't necessarily evidence, or there's particular benchmarks that'll just say, hey, look at this operation and how well we sum this. And so in order to try to be a little bit more fair and get a more complete understanding of what Bodo is capable of doing, we took the TPCH benchmarks, which are a set of open source benchmarks meant to be in sort of data processing space from SQL, and we translated them into Python so that they could run with Bodo. And this is an open source GitHub pack so that you can see exactly how we did this conversion. And then when we did this, we compared how Bodo performed to running these with Spark, to running them with Dask, as well as running them with Ray. So the first are our comparisons to Spark. And we ran this with the scale factor 1,000. So again, that's if all the tables were loaded into memory, it would be about 1 terabyte of data. We ran this on 16 C5N 18X large AWS instances. That's about 576 cores, 3 terabytes of RAM. And we use this Elastic Fabric adapter, which is freely available through AWS with machines of these sizes. And it is really efficient networking, basically. And what we found is that when doing this, Bodo is 23 times faster than Spark is on average. And in the best case scenario, we saw it as high as 65 times faster. And if you look at these numbers and compute them, that's roughly 90% infrastructure cost savings that comes from using Bodo as opposed to Spark. So if you're spending $100,000 as your AWS bill running Spark jobs, it could be down to 10,000 with Bodo potentially. Next, we compared to Dask. To be completely transparent, we're not by any means claiming to be Dask experts or as experienced with Dask as we are with Spark. But we did have our results validated by Dask experts. In fact, Travis Oliphant looked at our results directly and he kind of signed off on them. So when we tried to run this in Dask, we weren't actually able to run the full 1 terabyte data set. Dask was only able to consistently load the 100 gigabyte data set. So we opted to use the same cluster size, but scale down the data by 10 times. And when doing this, we found that Dask wasn't necessarily appropriate for these workloads at all. But it was on average 150 times faster, up to 500 times faster. And in one of the cases, even though we had 3 terabytes of RAM available, Dask still wasn't able to load all the data into memory. And it just hung. And again, we're not experts, but we did quick search on this, and it seems like this is a fairly common problem with Dask. So we don't think we've run into any fundamental issues in how we did this. And in all fairness to Dask is, from what we can tell, really good at doing scientific computing where there are more independent tasks, and isn't necessarily as well suited for these type of workloads. And finally, we tried to compare to Ray over Modern. Again, we're not Ray or Modern experts, but when we tried to do this, we couldn't actually get this to load for anything larger than 10 gigabytes. And our understanding is that Ray is originally built for reinforcement learning, and we just believe the data engineering support, it isn't ready, so it's not fair to really do a serious comparison at this time. But we believe that Spark, which is a very mature project, I would say, has put a lot of effort into improved performance, kind of shows the threshold and the upper bound on task scheduling systems. So we believe that even as Dask and Ray's projects continue to develop, that the Spark numbers that you're seeing most likely represent sort of a threshold for how good those projects can become, and really is the fundamental difference in the types of parallelism. So now I was going to go through a demo and kind of show what Bodo can do. One thing I do want to say is I mentioned our website earlier for tutorial. So our website is the same as our name. It's bodo.ai. And on that, you can find a bunch of information, including how to install our community edition. So our community edition is an Anaconda project that you can download and you can run for free on your laptop for up to 8 cores. And so if anyone is interested in trying this out, we definitely recommend going through our tutorial first. But we'd love to have you, give our project a chance and reach out to us and give us any feedback that you might have. But now I'm going to switch over to my demo. I do see a lot of activity in the chat, but I'm going to do that at the end if that's okay. So let me share my screen. So can people see my, what is it, Safari tabs?
Yes. Yes, we can.
Awesome. Awesome. So what I'm doing for this demo is I'm on the Bodo Cloud Platform, which again is the SaaS service that we offer through AWS to efficiently run your clusters. Because again, it actually is pretty hard when it comes to trying to maintain infrastructure for running things across multiple machines. And so here we have 4 C5 4X large instances, and that basically means we're going to be running things on up to 32 cores. And so I have a couple of Jupyter notebooks that I kind of want to show off that'll show a little bit of what Bodo can do. So for this example, we kind of want to show one of the fundamental differences that a compiler-based solution can provide in comparison to just a a regular library-based solution. So here, I ran some of these before this presentation to make it a little bit shorter. Here we generated a data frame with 50,000 rows, and there's this Python function that we want to run. Essentially what we're doing is we're computing a user-defined function in order to create a column, and then we're assigning another column, and we're just going to write this output. But if you're an avid pandas developer, you know that using df.apply can oftentimes have really adverse consequences because it's not one of the direct library kernels that are used. So running this in Python actually takes 20 minutes, I believe. And again, I'm going to save everyone the time. I'm not going to try to run this right now. But if, on the other hand, I run this with Bodo, we can see that Bodo is much faster in this use case. It'll just take a second. Yeah, and running the actual compute here, again, we're not timing the write to IO. That took, 4.3 seconds to run this apply, right? In comparison to 20 minutes alone to run the apply. One thing I want to make really clear, we're not saying we're a pandas alternative. We're not saying switch away from pandas. We're not saying that, we're the pandas solution on one core, but this is a very clear example of where pandas struggles because library-based solutions are only able to optimize the library kernels that they offer. And when your real code requires, user-defined functions that have to be applied across your data frame, that's where a compiler-based solution can offer a lot of advantages because we compile that user-defined function the same as we've compiled the rest of the code. So all of the optimizations can be natively built in. In addition, when we add this, PX here, which is some IPython magic that enables us having the ability to run this across our cluster and on 32 cores, it continues to get even faster. So you run this, and you see it takes 0.126 seconds to run across 32 cores. So went from potentially 20 minutes to, an eighth of a second. The second thing I want to show is just an example of, what we can do with our Snowflake adapter and what we can do in order to provide optimized Snowflake queries. So again, like I mentioned before, we're partnering with Snowflake. Our goal is to provide the most efficient compute possible. So when you have a workload that's, part Pythonic and your data is originally in a SQL database, we want to do the most efficient things to do in Snowflake, directly in Snowflake, and the most efficient things to do in Bodo. And that's our ultimate goal, and that's what we're trying to provide. So here we have an example. This is very similar to the example I had before, where you're loading a table. You have a couple of filters, one of which is dynamic, so it's not just like looking at like static literals, and then it's going through and it's loading a single column. So when you run this, when you actually execute it, you're going to see that after some amount of time, you're going to get quite a bit of output. So to kind of search for how long this took, I'm actually just going to search for it. Yeah, and we're going to see here that it took about 4.6 seconds to run this. And if I go over to my Snowflake tab here and I hit refresh, what you're going to see is that the query generated does in fact only load the table in question, despite the fact that the user query selected all of them, and that the filters that were applied are directly here in the Snowflake query. And then, just for comparison, so the way that we're able to do this is we're able to determine, how the filters are being used and what table, columns are actually being used. If there are situations where all the columns need to be loaded, we have to load all of the columns. And so in this example, we're printing the data frame before we actually go through the process of, going through and applying this filter and selecting a single column. So in that situation, the only thing to do for correctness is to load everything. And this is a good example, showing that we're doing the right thing, but also it becomes a pretty relevant comparison in order to see, exactly what the difference this can make when you're potentially loading, a fraction of the data on a query. And let's see, hopefully this is, okay, so here, this is the, okay, that was right there. Yeah, so you see the execution time without filtering, we're talking about 12.5 seconds, right? So there's a very significant difference. And again, looking at my history, we can see that, we had to load everything. So we're loading, 16 columns as opposed to one that's potentially been filtered. So yeah, that's what Bodo can do. I'm happy to take any questions. I'm not exactly sure how I should proceed through this. Should I just go through the chat, or what's the best way to do this?
Yeah, maybe if you're somebody that asked in the chat, maybe can ask directly. Maybe it might be a little easier.
Sherry asked about decorators, and I put it in the chat about the decorators, but I cited your actual documentation.
Yeah, maybe if you
Okay,
can
yeah.
ask it again. Yeah.
Yeah, so I'm just catching up on all of these. So will you share what the Bodo example decorator was and how it works? Yeah, sure. So let me pull up this example. So what is this decorator exactly? So the Bodo decorator, what it does is this essentially is a function that ends up compiling the body of this code being done. So we have a compiler that runs through several different stages through the process of essentially generating an MPI binary. And so what that consists of is this, starts off with the Pythonic bytecode. It runs a variety of optimizations and, processing steps in order to determine, a efficient runtime implementation that's an LLVM. And then it goes through the process of, having that executable be what actually runs. Does that answer your question? Does that explain it? And one thing I also want to emphasize, because I don't think I explicitly said it, is so Bodo is a JIT compiler, which stands for just-in-time compilation. And what that means is that when you call this Python function, it gets compiled with the types that are available at that time. So as you know, Python is not a statically typed language, right? You can have a variable X and it can be a list, it could be a number, and you can just switch them back and forth. And so just-in-time compilation is the way to compile individual functions once you have that type information for a particular variable. And as long as the types are consistent, you can reuse the same code. If types change, you have to recompile.
Yeah, go ahead.
So I see. So the question about how to identify the decorator. So effectively, the way that this decorator works and the way that decorators work in Python in general is it's essentially as though when you call F, you're actually calling the decorated code first. So a decorator essentially goes through the process of, it gets called first and then it processes the code that's inside there. I believe that's how decorators work. I might have gotten some of the details wrong. Someone can feel free to correct me if I did. Yeah, Alan, do you have a question?
Yeah, one question. So I'm more of an infrastructure DevOps engineer, but at my company, I work with a lot of Python engineers. So I'm a little bit out of my element. We at one point had a potential project where, in a nutshell, we were going to attempt to run 1 million Dask tasks in one go on a supercomputer. And then we followed through some case studies of other individuals trying to do similar things. And they found that Dask was incapable of doing more than 7,000 tasks before it became inoperable. And they extrapolated that at most it could do 12,000 tasks at most before it just basically would explode. With Bodo, or Gretchen, sorry, and with Dask, we found the main problem was that it had, which you alluded to in the beginning, or talked about in the beginning, was that Dask had a single point of failure, which was the master controller that had to do all of the pre-compiling of breaking up the different tasks. And that was way too much overhead for one module to do, one system to handle, and then hand that out to all the workers. Does Bodo solve that problem? Do they allow for either more decentralized computation for the parallelizing of a job, or do you? I guess I'm trying to ask, like, what is the scale that this could go to? Can you do this on 50,000 computers?
Yeah, so we believe so. We've done this, for example, on I think like tens of thousands of cores when we've run through examples of this. In terms of like the problems that can arise, there's, I'm trying to understand exactly what your job situation is. If there's, just enough code to constantly have to recompile, it does take some time to compile. You can pre-compile things with caching. We have that capability. And so from that perspective, we 100% think things will work, and we think things will scale. If you need to generate enough code in order to make sure that, everything is, be basically artificially like inflate the runtime, that'll increase the compilation time as well. In terms of, scheduling tasks in general, if you're, trying to deploy this to like a task that, or a big job that can be scheduled across, huge data sets and huge machines, we don't 100% think that Bodo will hold up. And, in terms of, can things fail? Things can always fail. That's always a possibility in a system like this. We believe that, with the scalability and performance that we offer, even when things do fail, there's the opportunity when retrying things, running things in Kubernetes, when, rerunning workloads, that things are so efficient, those become more feasible than before. And we don't believe there's any fundamental bottleneck to scaling that comes with Bodo. Does that answer your question?
I think so, yeah. Is your information available for contacting for Bodo, or do I just go to Bodo website?
So you can definitely go to the Bodo website. I can also post my email in the chat. And most likely I will forward you to someone who can speak with you and give you more details about, getting started with Bodo and, helping test this out.
Awesome, thank you.
Yeah, well, thank you.
I would like to.
Sorry, Sherry, I didn't mean to message you directly.
Nick, I would like to jump in here for a second because the previous question had to do with something that doesn't seem right to me. I'll explain. I'm using Dask on a regular basis, and this is why I'm very curious about what Bodo can do. But beyond that, I currently have a machine here that runs tens of thousands of jobs. So the bottleneck is not what the one he described. And there are ways with Bash to actually, you said this yourself, pre-compile some of the things and schedule their hands-off some of the pre-compiled elements to the nodes. When you're actually distributing over nodes, there is some elements that you do want to optimize if you're doing it, and probably the team there didn't know about those. So now my question is like to you. So each one of those parallelization system has its own small hiccups. Like here, when I used Dask in the past, and it thrown in an exception because it couldn't pre-compile some of my stuff. It actually also gave me some hints about what to do. It says, "Oh, you're doing this. You might want to do this." And once I followed the instructions, all of a sudden things became faster and better. So my question to you is, parallelization is not easy. It's actually hard. You're saying that you're showing it as if it's like magic, but we both know that there are some elements that are hard, especially if you compile everything to machine code and you cannot handle your exceptions well after what happens. You don't see the Python code that runs afterwards easily. So my question is, what tools do you have to actually help people that do want to make that jump? So tell us about more what Bodo can do for us in that perspective.
Yeah, so I think on the first point, there's definitely an aspect to which when going through a presentation like this, there is, the devil's in the details, as you would say. So nothing in parallelization is 100% easy. There are always situations where knowing your use case will be more effective than, what any system can do by default. In terms of when it comes to being able to run your workloads with and make this process simpler. So one thing that I think is really helpful, just to start off with, is again, we have our SaaS platform. One of the biggest hiccups that we've seen with people getting started is, configuring an MPI environment, even going through the process of creating, something that can work as a configurable cluster. And so as a result, we think the SaaS platform, number one, can be a great tool. In addition, we have some information and some examples available on getting started with Kubernetes as well. We think that deploying things with Kubernetes can help to kind of improve this process. And in terms of, improving your process for how you could rewrite things and how you can improve things better, we try to handle this in terms of how, we go through our error messaging and whatnot. We are a compiler, and as an aspect of that compiler, if there's something that we can't support, ultimately we can't support it, and that's the detail of it. And we work with trying to help you develop alternatives, as well as trying to make sure that error messaging and helping to understand why that's the case is clear. We try to do this through sort of our explanation of where the typing issues arise from. At times there can be issues in terms of where parallelism arises from, because you can essentially, for example, write completely sequential code, and when that's the case, we notify you like, hey, listen, you're trying to deploy this at scale, but the code that you've written is fundamentally sequential and needs to be modified. And then we try to supplement that with materials with learning materials, and we're continuing to grow these in terms of how you can use Bodo more effectively. So you're 100% right in terms of it's not just everyone's going to have the same experience and it's going to be simple. And there is a learning curve that comes with this. But we believe that when it comes to learning Bodo and helping to overcome the issues, we believe that those issues more or less can be improved faster than other systems like Spark and Dask, and also can be more effective as solutions. And in terms of things like failures, we've been running production workloads, for over a year in various companies, and we haven't had any failures that weren't related to code being unable to compile. Once we have it running, it was fully working and it was fully successful.
Okay, I have one more small question. You basically you decorate your functions that you want to run to Jitify. This means that you cannot run whole modules or something easily. It's actually, Dask also has some elements there, but it's mostly solvable there as well. But this also leaves the fact that if someone uses like globals and things like this, you basically things get stuck, and many people just don't write efficient code. Do you have any magic solution for the globals? And by the way, I can tell you like PyPy throws exceptions there. There was a PyTrans, I think they also complained. It also everyone who tries to optimize Python falls on globals. So do you have any magic solution there?
Yeah, so there are some things that are involved with globals. So one of the fundamental ways in terms of how we handle globals is that globals are treated as compile time constant at the time. So if you have let's say you have a big array that you're using and it's directly as a global, that gets lowered as sort of a constant array and it's treated as a read-only object in that situation. There are various situations for it. Oftentimes when it comes to globals, it's less so a situation, at least that we found, where it's like someone trying to do all their processing in globals. It's more so you have a few constants, you have a few key things, you have your logger API, and those are what end up getting brought down directly into your processes. You're absolutely correct in the sense that you shouldn't try to compile your entire module with JIT. While we're using Python, we are not a pure Python accelerator, accelerate everything about Python. We are focused on data analytics. We can optimize the data analytics components of your workload, and Python can be completely great for the various scripting details that can be done outside of data analytics. And in terms of ways of improving the globals process, I think that's something we're also looking into to continue to see how we can grow this process. And by the way, like I think I mentioned it earlier, we use Numba internally as part of our compiler toolkit. This is stuff that comes from the Numba open source project. If you are interested in contributing to this or you have interesting ideas regarding this, we'd love to hear about it inside of Numba. So if you have any more information you'd like to learn about that, I also encourage you to go there as well.
Thank you. Thank you.
Hey, Nick, I have a question. Have you guys looked at like PyTorch or any of the neural networks and accelerating those? Is that even applicable? Because that's where I spend all my time.
Yeah, so we looked at that in some detail. So when it comes to things like PyTorch and TensorFlow, what we'll find is oftentimes those are compiled code. So when it comes to running things on a single machine, those tend to perform pretty well, and there's not a huge need for acceleration necessarily. Where we believe Bodo can provide some support is when it comes to scaling those across multiple nodes, which is, again, I think where things to get. Yeah, right, so we have some integrations with Horovod so that you can go through the process of running models across multiple nodes at the same time. So I would say that's not as developed or as invested in some of our pure ETL work in terms of pandas and NumPy, but that is an area that we could explore and we have some existing work on, and we hope to continue to grow in the future.
Right, and sitting around waiting 30 or 40 minutes for your model your learning set to compile is not fun.
Yeah, no, definitely.
So I could see parallelism. That's really interesting. We'll have to talk offline. Thank you.
Sounds good, Dave. Thank you so much.
Hey, one question, it's Mohammed. If you're using Python bytecode as kind of your input to your JIT, how do you handle code from an extension module? For example, NumPy that's defined in C. How are you able to take that code and do your MPI magic on it?
Yeah, so I want to clarify some details about this. So when I say we take the Python bytecode, we take the Python bytecode directly of the user's function right here. When it comes to something like NumPy or like pandas, what we have is we have internal kernels implemented that provide that functionality in a truly parallel fashion. So again, I encourage you, if you want to curious about like how a NumPy function is implemented, a lot of those are in the Numba project themselves. So you can see situations in which say you're doing like np.arange. There's details in terms of how do you have a matching implementation that could be done essentially in Python, but then that kernel itself gets compiled. And so it, as a result, produces, an efficient equivalent kernel. These projects are all open source. And so one of the benefits of that is you can go through the process of being consistent with exactly what they're doing. But it's, we're not trying to find the locations of all the packages. We're not going through the bytecode to try to, find all the details. We do ultimately look at the semantics and at the functionality of those implementations. Does that answer your question?
Yes, it does. And if I could have another small question, I've done some HPC work with computational physics, and one of the things that's fairly common is kind of customizing the hardware or the kernel, so you can turn off timestamps in file descriptors. You can change the size of the memory pages or the file system pages. So are you doing anything like that in the cluster to kind of squeeze the most out of it?
So in terms of all of the specific details of like each cluster instance, there's a few things that we do that improve this quality of computation. So we're using, I think, Intel MPI in particular on the cluster right now. We found that performs fairly well. The scheduling of processes themselves tend to have an impact that can be pretty significant. And we put a good amount of effort in there. As well as we've also done some additional work in terms of, trying to think of all the details, in terms of some of the network interfacing as well. So like I said, when you support that elastic fabric adapter inside of AWS, which we can integrate with, that gives us the ability to essentially, you kind of like bypass TPC. It's like a very efficient networking where you're doing it like machine to machine. And when you get to communication, those can have like really big impacts. In terms of some of those like smaller system level changes where you would go through the process of like actually like manipulating page sizes, at this time, we're not doing anything of that nature.
All right, cool, thanks.
Thank you for your question, appreciate it.
So I do have one question related to the like the cluster itself. Like on Spark, you have, of course, you have the master and you have the worker nodes and all that. Like can you give us like a very broad idea like how the cluster itself is being built? Like do you have, is there like some central machine that sends the code, or I don't know? Can you kind of give us an idea how that works?
Yeah, so as a full disclosure, this is not where I work actively day to day, so I might get some of the details wrong. And I know that our SaaS platform is something that we're evolving in the coming weeks, so there might be some changes that are running here. But at a high level, what we currently have here is, so we have, this series of nodes that are constructed here. And when you do this, it's deploying the set of nodes inside of my AWS account. It's deploying with a security group. It's deploying with a networking group in order to have them able to communicate. And it launches instances of IPyParallel, which is a project by Minreg and Kelly that we sponsor, and is a process of basically doing parallel computation across nodes through Jupyter notebooks, basically. So when you launch this Jupyter notebook here, this is at the time, I believe this is currently run on its own small instance, but I think in a future rollout in the next coming weeks, we have one. It's just going to run directly on the cluster itself. And so what this process does is there's essentially a set of processes in the background. I could probably show you. There's a set of processes in the background that are essentially orchestrating sort of like some engine details in terms of like keeping track of what's being run and what's being deployed on each machine. And so then behind the scenes, we're essentially orchestrating through MPI this communication between all of these various nodes. And they're each basically running their own Python process that is maintaining this information. Does that answer your question? So there isn't necessarily a management node that keeps track of all of these.
Yeah, and I do have another question. So is this something that it can be installed on your infrastructure, or is it like, I know like Spark, you can download it and you can put it on anywhere you want? Is it Bodo, something like that, or is it like you have to go through the bodo.ai and then you point to the cloud provider that you want to use, or how does that work?
Yeah, so in terms of just getting started, when it comes to, we have a Conda package that's available. I believe it should be available on pip on most instances. I think we're still rolling out the M1 version. So, but if you're on like an old Mac or you're on a Linux or a Windows machine, there's a pip installation that you can do to get started. And so from there, you can run things directly on your machine with Bodo. When it comes to actually scaling to your production workloads, we are a closed source project. We have limits in terms of the number of cores you're able to use for free. And so you can contact us about if you want to integrate us into your on-prem system. We will work on any of those various cloud providers. It's more of a matter of just making sure the licensing information is in check. Alternatively, there's a usage process by doing this just through our SaaS platform instead. And we can extend free trials as needed for all of this stuff as well. So please just contact us if you're interested. Does that answer your question?
It does. Yeah. Thank you.
Awesome. Did I miss anything in the chat? Yes, message passing interface. Okay, I don't see any more questions. Lauren, I'll pass it back over to you.
All right, well, thanks so much, Nick. This was a very, very interesting talk, and then definitely a very interesting project to take a look at. So again, thank you so much for coming and presenting to our community in such a short notice. It is truly appreciated. So thank you.
I'm very happy to be here, and I appreciate you all listening to me speak.
All right, so I'm gonna stop the recording now, but stick around and we'll go from there. So.